Recording in progress.
All right.
Anything else?
A spotlight room, go to 851 and more spotlight for everyone. That brings him up like this. You go. You're good. That brings him up like that. So anybody in the room can just see him. You good? All right.
All right.
Can everyone hear me okay? All right. Welcome to recitation 6. That will be taking you through classification and verification for CNN. Basically, this will help you in your homework 2, part 2, and also in other applications where you need to use CNN for such type of tasks. So I think this should be updated. Let me go to Piazza Post. All right, so the first thing we want you to do is to go to Piazza Post 580 and have the notebook downloaded from there. Here is Piazza Post for this lab. You can get the notebook from here. Advise, don't make changes on the notebook, just have it downloaded or make a copy of it, and then you can work with that. And I'll be taking this lab with Siobhan, and then our plan is to review the core concepts behind CNN, focusing more on face classification and verification, which is the main task in the second part of your homework 2, and also to build a kind of a small CNN for a faces data set. So let me see a thumbs up for those that have already made a copy of the notebook, and then we can go ahead. If you've done a copy, can you just indicate if you've done that already? We see a count and then we go ahead. You can see a few more people. Let us know if you've done a copy of the notebook and you are ready to go. And also, why we expect that you go through the notebook with us, we also expect that after you've completed the checkpoints, there are checkpoints in the notebook, which are tasks that we expect that you follow up with us and then you complete it along as we are going. So, and when that is done, you can, after the recitation or even within the recitation, you can fill out the poll on Piazza to corresponding to the checkpoints you just completed.
Yeah, I'll do that now.
All right, guys. Now that homework 2 is released, it's been about a week. I hope everyone has started working on it. And yeah, this lab is correlated to your homework 2 part 2 so that you can have some hands-on exercise so that it'll help you kind of build on the homework 2 part 2 homework, which is literally face classification and verification. So if you haven't already downloaded the notebook, it's on the Piazza Post 580, and we can go through checkpoint by checkpoint and make sure we have some hands-on experimentation regarding face classification and verification. Okay, what is a classification and a verification problem? Uh, a classification problem is given a set of images, does this image classify as an image of a face? It can be any classification. We're just talking in perspective of face in our problem, but what I mean to say is that does this classify as a face? Does this image contain features, patterns such as nose, eyes, forehead, lips, ears, and all that constitutes as a pattern recognition for face. So if all these constitute together, this, pardon me for my voice, yeah, if all this constitute together, it is kind of a classification problem. And given an image, who's this person? Is this person an X, Y, or Z? And that is what we are trying to classify. You can see here in the example. And of course, this has this used in a lot of application like attendance systems and etc. And a verification problem is given a pair of images belong to the same person or not. And again, we use this in unlocking of phones and etc. But this is what it makes much more complicated in our homeworks. When we are doing classification, we are performing classification on the certain data, and we are kind of moving the same data of classified data into the verification problem. That is why you might see a lot of hindrance in accuracy, but you will understand as we move ahead in time and make progress to see how you handle such challenges in your homework. Well, we can see here first you have to make your checkpoint 3. You have to check if you have a GPU, which is just NVIDIA SMI, and that's your checkpoint 3. And we will this is the checkpoint 4 is from the last week's lab where we just trying to establish basic convolutional. We are showcasing how a convolution takes place in the given example. And we can see here there's an image pattern which is in the form of array, and a kernel size of in the form of array, and this kernel will convolve, which is scanned through the image and produces feature maps, which is an extraction feature which we perform the further um, anything that we decide to make that use of. But the process of convolution is at the most basic form that we can make it as an understanding. I hope this is fathomable, but yeah. So when we see here, it's in the form of an image, and the kernel which will scan through the image to produce the feature maps. And the feature maps you can see here, it is also is presented in the visual form where you can see the weights and biases produce a certain grayscale image stating, the extraction of features, which is a pattern recognition which is made by the kernel while scanning over the input image. So that's your checkpoint 3. Sorry, pardon me. It's 4. And yeah. I'll give you guys a minute before we dive into the building of face classification and verification problem. We are going to do this on a small data set called LFW, which is kind of a small toy data set which contains numerous faces, around 2000, if I'm not right, if I'm not wrong, close to around 2000 faces, and we kind of perform face classification and verification on this data set. So I'll give you guys a couple of minutes, and before we just dive into the classification and verification problem.
What I am thinking is to give some time to go through the concept. And after that, before you really speak, okay, this is and we post the reference.
Okay, guys, let's continue. Yeah, the cell makes you import all the necessary libraries and setup. You just have to run the cell, and you don't have any other checkpoint. And after that, that's your checkpoint 5. And like I said, this is will be loading the data set called LFW, which is a people face data set, which contains about 2000 images in whole. It's a beautiful toy data set to play around with. So that is what we'll be implementing in our uh, lab today. Yeah, so as I speak, so we import LFW dataset, and we produce the shape. You can see here you have to, there's a small to do for you guys. You have to print the shape and the number of classes. It's around 1560, and we'll be taking the minimum number of faces per person, which is like 50, so that we'll have a better classification accuracy, so that there'll be at least 50 faces of the people in the data set that we extract faces from. And we kind of resize into the factor of 0.4 so that we can have it. We do not exceed the computation. I mean, we really do not care about the computation because it's a toy data set, but just trying to resize so that we can include everything and reduce the factorization and normalization. So yeah, there's a small to do for you guys. That's your checkpoint 5. And the next one, we will be plotting some sample images. You just have to run this cell. There's nothing to do here, and you can see here that there are samples of faces, which you will see. So yeah, let me give you a minute or two to work on this, and before I continue, and yeah, we'll be here in case you need something.
I'm sorry, quick question. Um, for the previous cell, if you scroll up a little, I think it says the number of classes is x dot size. What's the difference between x dot size and like target names dot shape? Because if we're asking for the number of classes, is that not like the people we want to categorize? Or maybe I'm getting just a little bit confused with what target names is.
You're right to a certain degree. This target names is what we are trying to target to match the data set names, which is in our data set. And the number of classes, that means we are classifying 37 people out here. That means there are 37 different people with at least 50 or plus faces in the data set, which constitutes about a total of 1560 faces in the data, which is images. So when we say X size, we are trying to constitute the minimum size of the 50 faces so that we kind of cluster them into 37 different people. I mean, that is what we are trying to classify, but as we proceed further, that's how the classification occurs when we convolve and set up and build on the architecture. But this barely means this is kind of extracting the different names which belongs from the data set, and that's how we see that number of classes, which is equal to 37.
So how come what's being printed out is like 2.8 million pretty much?
Oh, that is after the uh, yeah, pardon me. This was I was talking about the dataset shape. Yeah, the number of classes would be classifying all the clustering of the features that we extract. Like just now, I mentioned, face patterns which constitute to recognize face, such as eyes, nose, your ears, forehead, lips, eyebrows. So these are the different classes that constitutes in recognizing a face, right? And which has to classify from a different face to a different, from a different person. So these classes constitute on based of these innate features, which classes out and categorize the features which we try to classify over time.
Okay. So in essence, like the 37 or something like that is like the number, like the actual number of people that we want to um classify, but the 2 million is the specific features that are helping us in classify them? Is that
Correct.
what's going on? Okay.
Correct. Correct.
Okay, thanks.
Yeah. So let me know in the chat if you guys are up till checkpoint 5 and plot some samples so that I can continue. I'll give you guys a minute or two again.
Yeah, I mean, the classes are some what I'm talking about the features which the will pick out, when I know biggest. So all these classes constitute, yes, you're right, it is the target classes. These are the features that will pick up.
That's true, but classes.
Exactly. Overall, we still the same.
Okay, let me proceed. Now we pre-process and we split the data set for our training and testing instances. We have to primarily normalize the images on 0 to 1 range and add a channel dimension. Um, this is basically done so that your model is regularized, pardon me, and we continue to one hot coding, which kind of adds a transformer for your Y encoder, and we split our data set into 80% train and 20% test data set. So we can see here when you print the training samples and test samples, we have around 1250 training samples and 312 test samples of faces, which we will make a model to train on. And the next cell is augmentation. Yeah, anyone can say why augmentation is necessary when we especially deal with computer vision problems?
I think it allows us or allows the model to be able to deal with potential invariance in or like the shifts, rotations, that kind of stuff that we could see in the actual image itself. I think one of the examples was like maybe if the flower that came in was slightly tilted, right? We still want the model to be able to know that that is a flower. So that's kind of what the data augmentation is helping out with.
Correct. We try to, pardon me, we try to make do augmentation so that our model is regularized and recognizes all the variants of the data in whichever form it may present, and so that we need a model to train over it. And it also helps in not underfitting or overfitting the model. So data augmentation is very necessary and quite a vital um, play. It plays a quite a vital play in computer vision problems. So um, I do encourage you all to implement as much augmentation as possible. In our example, we can see here we have a rotation range of 15 degrees. That means your images is rotated to a 15 degree so that your model recognizes even despite having a rotation of 15 degree. And there's a wide and height shift range that basically means it's shifted. I think it's by a certain factor so that the images is cut off, but yet still the model recognizes, should recognize while we train. And there's a shear range, which basically is a shear transformation with a certain degree, and a horizontal flip, which is literally flipping the images. And there's a zoom range of certain factor, which zooms the images. Yet the model should be capable of grasping the pattern recognition, which is necessary to in order to make the classification or any um, target classification problems or prediction problems. So once we do that, we pass that onto our train and test data set. And you can see here, which is with the batch size of 32. And we augment all these into our data set. It is randomly initialized to the images.
Oh, sorry, quick question. With regards to the data generation, so the fact that we apply a rotation of 15 degrees, does that mean that every single of our um training data gets like every single image in our training data gets rotated by 15 degrees, or is this kind of like a randomized process? Like, and
It's
every
a
single image may be between 0 to 15 degrees in rotation.
It's a randomized process, and it's not a range from 0 to 15. It's like one image might be 0 degree, another image might be 15 degree, and it's
Oh, okay.
randomly initialized. And
Okay.
again, with all the other features, it's randomly initialized when when we talk about zooming the image or flipping or any shift ranges. All these are randomly initialized by picking the random samples from the data. So it's not particular, or not everyone will be implemented with certain augmentation. So it's like randomly initialized, if that's your answer question.
Okay, thanks.
Yeah. So we move on to building an architecture for CNNs. Let me give you guys a minute before I dive into this.
Oh, sorry, one other question. So which one is the next checkpoint? Because I see maybe this notebook is outdated, but build the second layer of the CNN. But is that not already given to us in the second convolution block, or am I maybe just like mistaking things?
Yeah, just need to refresh. And people who haven't made a copy, please do, because your changes are being reflected here. Some people are making changes already on the notebook, and it's been reflected on the, let me see. And you can skip that because it's already completed. Basically, what we wanted you to do is the checkpoint is, this is the second one. Basically, what we wanted you to do is to build this the second convolutional block here, which is quite similar to this, but just an upsampling from the first to the second block. So uh, what you do rather is just complete, think about what this layer outputs, and then you complete that here, and then you can you can just get your results from here and pass it to the model builder, as well as also print out the model summary, which will
Okay.
look which will look something similar like this.
Ah, okay, okay. And I see that your model that you have has dropout, for the like the flattened part of the model, and then but you also have batch norm for the convolution. So when it comes to CNN kind of models, uh, is it sort of true then that having batch normalization and dropout um is fine? So in essence, like they won't cancel out each other's effects?
Uh, you wouldn't say that it cancel out. It's just like maybe you're doing uh, so much of regularization, uh, and I think Prof would, or has talked about this. Uh, I don't know if he's done that already in your lecture notes. When do you decide? Say you have both, say dropout and that you apply both of those regularization things. What you said is okay. It's like you're applying too much of regularization, which
Mm,
one,
okay.
yeah, one can also work. Yeah.
Okay, because I think I remember him mentioning for MLP, so maybe not necessarily this type of model architecture, that one like does something, I think, to the variance or whatever, and the other kind of does the almost opposite type of effect. So they could potentially clash. But I guess since the convolution here and the like
Yeah,
flattened layers, they're separate kind of, so it probably should be fine, I'm guessing.
yeah. Both of them can work together, but like I mentioned, is just like uh, too much of regularization. You're doing dropout and then so if it's just like too much of regularization, which you can also use one. But just for the sake of completing this, yeah, you can have both of them, and they also work. Uh,
Okay.
yeah,
All right, thanks.
you have some time to complete that, and then you print out the summary. Uh,
Pardon me for that. So yeah, now we build the CNN architecture. We can see here we have 3 convolution blocks, and before we flatten out and pass it through the final layer. But yeah, I guess if you guys refresh, we would have wanted you to build the second convolution block. But either way, try implementing it, and I'll go through what we are exactly doing with each layer. We can see here we are trying to uh, pass. We have 3 convolutional blocks with ReLU activation and kernel regularization with batch norm and max pooling at each layer. And we can see here when you print the summary of your model, we'll be dealing with the total parameters of 226K with the trainable parameters of 225K. And that's your previous checkpoint 7, which you will be printing the summary of your model. Now we move on to training the model. You can see here we'll be using an Atom optimizer with again the basic cross entropy loss, and we'll be measuring accuracy. Again, we can play around with these things. I encourage you guys to implement different optimizers. You can even include the schedulers and play around with different loss functions, which you guys are already implementing in your homework. You guys will face much more challenging outcomes in your homework, but this is kind of the fundamental go through so that you guys are comfortable with the homework 2 part 2. Let me know in the chat if you guys running any hindrances so that we can help you with this. And once we do this, we can say that we are almost done with the classification problem. We trained our model and tested with our accuracies to see that how the model is performing classification. Here is an example. It's around 70% accurate, but yes, this is uh, running with less epochs. But if you make more changes in the architecture and the hyperparameters, we will be able to exceed very good accuracy.
So is this process, because I think, for example, for mine, I think due to early stopping, it stops on epoch 10, maybe. So is there like it seems like there's maybe an element of maybe like luck as to where your like starting point gets initialized as to when, you get the early stopping to hit? Or is that why, like, because mine stops at 10 out of 15, right? So that's because of the early stopping, if I'm not mistaken. Or is that because of something else?
It is because of the early stopping. It is mainly because I think because of the yeah, I think there is a threshold that we are passing through. So if it is not improving after a certain point, uh, perhaps how much it is ought to improve. I think if there's a little bit of threshold that is kind of stopping, we just didn't want you to run a lot of epochs and kind of go through it a lot. So I had it a little bit of threshold so that if the model is not improving by a lot, it stops before it
Oh,
reaches
okay.
the entire epoch range.
Right.
This
Okay.
implementation is also helpful in your homeworks. It's a very tricky way to tackle, especially whenever you're building a model and working on it, because most of the times you'll see that you'll be running your model and it's barely, you'll be running on X number of epochs and the model is barely, performing or increasing the
Right.
accuracy or decreasing in the E or whatever the metric is. So
Mm-hmm.
at such situations, if you kind of have a threshold that if your model is not performing, or if it's not exceeding by a factor of certain degree, then you might need to stop training. One, this will save you a lot of time. This will save you, and two, this will save you a lot of compute. And three, you can get to know how much it is performing, which how much of a compute and performance you are putting the model through. So this technique is kind of encouraged to students so that they follow this, so that you just do not keep running your models and hoping it might, kind of exceed the expectations later on, while not in the current performance. But ideally, it won't be the stage, but because when your model's performance is deteriorating, it's most likely to go down or not come back up unless you have a very bizarre change in your hyperparameters later on. But this is kind of a technique where you try to implement so that it's very optimal in terms of majority of the perspective.
Okay, I see. And so, I see that the early stopping and the scheduler have been applied on the validation loss. So, um, I guess two questions here. Is there any sort of difference between monitoring accuracy versus loss? And also, um, w- is it just very common practice to use validation rather than training, like loss, for example?
It's pretty much a common practice to use validation in terms of inaccuracy and loss problem, but we do implement both accuracy and problem. It's just a different way of metric measurement, which we are going to be implementing. So it's it's kind of a personal choice on what you really want to be the metric of evaluation and set a benchmark for. But this is a common practice. Like we said, it's just like a fundamental kind of a go through a lab so that you guys are kind of having a familiarization before you dive into the homework, before you dive in
Okay.
deep into the homework.
Right. Okay, cool. Thanks.
You're welcome. Okay, now we move on. I'll give you guys a minute or two.
Of time. We're almost at the end, so. Probably technical.
So until now, what we did was complete classification. We will kind of do a demo verification now, and yeah, let me proceed. And now here, before you enter your next checkpoint, you can see here we are kind of creating a submodel for the face embeddings. Why do we do this? Um, this kind of takes the embeddings of the faces in our example for today and kind of creates a model with a certain necessary features which has the faces, which we will be extracting these embeddings for the verification purpose in the next step. So why are we doing this? Why not just take the whole image and just do the verification? You may do that if this was a billion parameter model then this would kind of be a very optimal way to do that, because you cannot take the entirety of the data or entirety of the most of the data and pass through the model for whatever your model performance is doing. So this is again quite an optimizing technique where you try to just take the embeddings of your model and create a submodel and then perform your model whatever is bound to perform, and then you kind of make an inference on that, which kind of upscales to the entirety of your data. Again, this also increases, I mean, this also helps you in having a very, pardon me for that, it helps in your computing power, it helps in time saving, and it's also a very good optimizing technique where you kind of deal with the problem at a large scale, especially at large scale. So we can see here our embeddings in the certain shape, and we then extract these embeddings, and we are using the cosine similarity here to determine how close the faces are for the verification task. And we pass through different two sets of images. Again, this is randomly extracted, and you have to, there's a last to do here for your checkpoint where you pass through the similarity function, and then you see the cosine similarity between two faces. And if it is, you can see here again we have used a threshold. If it is greater than 0.75, then they're most likely to be the same faces. If it is less than 0.75, it is very unlikely to be the same face. In our example, it's just randomly extracted. You can see the cosine similarities between the two faces, which was randomly extracted, is 0.996, which is like almost identical, which kind of makes us the inference that the faces are likely to be of a same person. So this is your last to do, which kind of gives you the glimpse of how the verification model works on the large scale. But this is randomly extracting just one image, but we will be doing this on a very large scale on your homework 2 part 2, which you'll be working on, which you're already been working on, to be honest. Yeah. So that being said, that brings to the end of your homework. Again, you can increase the threshold here. You can play around with a different measuring function. You don't have to use cosine similarities. There's Levenshtein distances, and there's multiple other problems problem statements which deal with the distance of how different one vector is from the other vector, because that is what we are dealing with at the lower scale. And have the performance metric do its function and see if our our verification performance is up to the mark. So this kind of brings to the end of your lab. You have to do the checkpoints and make sure you mark those checkpoints on the Piazza post as well, which is, I believe, 580. And make sure you mark all these checkpoints. We also have a solve notebook that will be uploaded in quite a while, so that you can have that as a reference. And yeah, if there is anything you guys want to discuss, now is the time. We can go through the discussions. Any help regarding homework 2 part 2, if there's anything that you want to need kind of problem with, we can talk and have a discussion for a couple of minutes.
I was kind of curious about kind of post hitting the early submission, what would be some maybe good steps to maybe like good next steps to try out. I also see in the chat Drew has a question of how long should training to reach early submission take? I mean, I think for me, because I upped the batch size, it was able to each epoch took around like 5 to 6 minutes over 20, like for each of the 20 epochs. But I think if you kind of keep the batch size at is, it might take a little longer. But
That is
yeah,
true.
so because I think one of the things I was wondering is like having hit the early submission, because I saw on the handout, right, you can try a bunch of different architectures, including something similar to ResNet, or you can try out um like different loss functions or different augmentations. And so it seems like there's a lot of different um possibilities that we can explore, but it wasn't 100% sure whether like UTAs have a recommendation of kind of like how it might be good to kind of approach this exploration, especially because I think the actual homework itself, the on-time deadline is a week from now. So I think we have maybe at least a little bit less time compared to last time to get things in. So yeah.
Yeah, that is just because of your spring break coming up. So we
Oh,
guys
okay.
don't want you to be overwhelmed during the spring break as well. So you guys
Uh-huh.
deserve the spring break. So that is why you guys kind of have to rush through the homework too. It's
Mm-hmm.
usually the same way during the fall as well, when before the winter break. Sorry, before the
Okay.
yeah,
The fall break, yeah.
fall break. We try to have this kind of like a 1 week early kind of a deadline, but this is
Mm-hmm.
doable. It's nothing to be that much of a concern, particularly. So, yes, we do come up with, certain recommendations on what you guys can try and to reach the high cutoffs and such like. So, but you guys also have to be very initiative. It's not like we'll just you guys come in and just ask for it and we just hand it over. You just have to show that you're having a well defined architecture, well defined model that's being performing reasonably well, and then we try to kind of help you up your game in the process. That being said, yes, there are very numerous things that you are kind of at the bay for, that you'll be trying, especially in this homework. So there's nothing to be concerned about to a greater detail, I would say. As long as your model is performing at a reasonable way, then we try to suggest and implement a well-defined architecture or hyperparameter that you guys can, use and implement to increase the efficiency of your models.
Okay, got it. Thanks.
Are there any other questions on Zoom? Well, this brings the end of your lab on CNN's classification and verification, which I hope kind of helps you guys kind of work on your homework 2 part 2 especially. We will be still here if you guys need any help. Uh, for a couple of minutes if you guys need any help with the homework, I mean the lab or homeworks, anything in general. And yeah, before we move on, so thank you.